The task we've given the teams is to take off from a moving vehicle, go to a search area, search for survivors, and then return and land on the moving vehicle. We did a few rounds of down selection and finally had to pick 10 teams to come to Rome, New York to fly for the final competition. Those 10 teams are going to do a great job at showing you really what's possible here with an M100, a guidance platform, along with their creative minds and software engineering skills.
This competition is a fantastic demonstration of a test case for a search and rescue mission using autonomous drones for flight. So imagine a disaster area where there's some number of people that you know have to be rescued, but you can't access it. So you're in an F-150, you drive as far as you can to the disaster area, hit a button on the truck, and then it pops off the back of your truck, and then it scans an area for survivors. And when it locates a survivor or a victim, it'll send the GPS coordinates back to the truck, to your little command central.
The reason we chose search and rescue is really because that's a problem that we think everyone can get behind. It's a clear need, and we think that drones are a great alternative to putting more humans in harm's way to go solve that problem.
Team Juju is up next. As soon as they get on that taxiway,
Materials back safely on the ground, and they're going to discuss some additional parameter changes.
How far off the back was it?
The front two propeller guards touched the bed of the truck.
But not the feet.
Not the feet.
0.5.
0.5.
We'll have one more chance. So 2.8 goes to 3.2, and 3.1 goes to 3.6, right?
Yeah, baby.
Okay.
All loaded up with the enchilada with
Yeah,
red
and
sauce.
I'm going to try and get it off before we lose line of sight of the search area of those trees. So if we could just quickly accelerate 15 miles an hour without losing anything.
And then we're rolling with Team Artero. We're giving the green light for takeoff. Artero prop spinning.
Team Artero making its way to the search area. Team Artero choosing to stay nice and low to get a better view of those survivors.
Have we gotten any survivors?
Oh, Team Artero detects the survivor in the rubble. Team Artero finds the survivor. Team Artero in a tight spot here. Can they squeeze through? Yep, they make it through. Team Artero searching through a pile of logs now for anyone taking cover there.
Oh, that's right by the opening there. Ellie, we need to have a decon. I can't kind of see it. I can't see it there.
Issues that will start moving command to the truck. And they're between 100, tracking the truck. Some wild gyrations there, but still tracking well. Camera's got the target in sight. Coming down about 6 feet, 5 feet, 4 feet for Team Artero. Looks well positioned on the truck bed. Looks like Team Artero. Oh, both. Oh, Team Artero with the retreat. 100 lands on the moving forward truck.
With its commercial drones and SDKs, DJI has created an ecosystem where software companies like Automodality can create amazing applications without needing to worry about the details of the drone platform itself. We think this is an important step forward in the technology because it allows us to focus on the domain-specific problems, such as locating victims in a disaster area with pinpoint accuracy, or using computer vision to stay just a meter above a row of vines looking for disease, or even flying under the canopy of a forest to measure how much carbon is stored there.
First, I want to thank DJI for inviting us here so we can tell you about all the cool things we've been able to do with their technology. If there's two things you should take away from this discussion today, one is that you can actually do some pretty interesting things with their SDKs, as you know, Darren and Rob are talking about this today. And two, I work on some pretty cool stuff. So, having said that, what I'd like to talk about today is some of the technology that went behind what you just saw in this contest, and how we're trying to apply it in the industry and what we've done with the SDKs and so forth that Rob and Darren have talked about. First of all, this was the team. This was the team that was in New York competing. Includes Dan Henage and Jimmy Holiday. And what I should do is first describe a little bit about what you actually saw. Obviously, the drone took off from the back of a moving pickup truck. It flew over to a search area. It was a 50 meter by 50 meter search area, you know, going through rubble. It had to search for survivors. These survivors were actually April tags about yay big. So they're pretty small, distributed around the rubble and the ground. So you had to fly pretty low to actually see it and use computer vision, the cameras on the M11, the Matrix 11 there, to M100 rather, to see the actual April tags. And then of course, computer vision to recognize them and then transmit their locations back to a mobile application that was running on the iPad. And then after you search for a while and try to find as many survivors as you can, and your battery is getting low, then you return back to an area and try to land on the back of a truck. Now, at the risk of bragging too much, I must say that we were actually the only team that found any survivors, and we were the only team that landed on the back of the truck. So we were actually pretty successful what we were able to do with that. So you got to be able to land on a truck, got to be able to search for survivors, that means sense and avoid sort of technology, you know, search through the rubble and so forth. You got to be able to use computer vision to recognize things. And so let me show you some demonstrations of some of the things that we did in preparation for the contest. So of course, landing on the back of a truck. This was actually the most difficult thing to do. It actually carried the most points. And so it turns out if you're going relatively slow, let's say less than 10 miles per hour, this actually is not a very difficult thing to do. We could do this all day long at less than 10 miles per hour. In the contest, we had to go up to 20 miles per hour.
Yeah, baby, yeah, baby.
So it turns out,
yeah,
if you speed it up a little bit, you start getting some aerodynamics from the cab of the vehicle, and bad things can happen. This actually was the last flight we did before we went to New York. We weren't actually even sure if the drone was still working when we got there. Also, as you might see here, some interesting aerodynamics start to occur as it gets down below the cab. But of course, we were eventually able to get it to work just about right. So that's landing on the truck. So that was one of the key sort of capabilities that we had to enable the drone to do. This is the actual run from the contest. We did 3 runs. The first one on the far left-hand side, it overshot the bed. The one in the middle, it undershot, and the one on the very far right, it hit it spot on. So you can see as it was tracking the April tags that were in the bed of the truck, it was coming down. Now, of course, as we're searching for survivors, you have to do sense and avoid. And so this is a little bit of a demonstration of the sense and avoid sort of things that we were doing, you know, at our lab, outside of our lab in San Rafael, California. We had a big debris field there with lots of trucks and so forth that we're able to, you know, try to maneuver around. Basically, for the sense and avoid, we're using some stereo vision cameras. There's a guidance system that you can purchase from DJI that you can attach to these drones, the M100s and the M600s and so forth. And with those stereo vision cameras, you can then construct models of the world, and then use that for path planning and trying to avoid objects and do sense and avoid sort of things. Now what you're looking at here is an example of finding the survivor tags. You can see the survivor tags are relatively small, and they'll be highlighted as it sees them in red. It sees the highlights in red, and then it transmits the location back to a little dashboard that we've got there. That was one of the capabilities that we had to do as well. Okay. Okay, so it turns out that when this contest was announced approximately a year or so ago, we'd already been working on a lot of these technologies well beforehand. And our objective in Automodality was to develop technologies that would allow drones to fly close to things, essentially for inspection purposes. In addition to being able to fly close, also be able to interact with remote pilots, perhaps through some sort of portal to allow them to do some sort of, you know, remote control of the vehicle, so to speak, not necessarily fly them, but the vehicle's flying in some sort of semi-autonomous mode, being able for the remote operators to be able to control them so you can potentially get different views of an asset and so forth and so on. And so our objective is always to try to develop technologies that allow us to fly close to things in a very autonomous fashion. And by the way, all the videos you're seeing here today, it's all totally autonomous. Push a button and the drone takes off and it's pretty much on its own. So this is, when I say close up to things, I literally mean within meters of objects and so forth. This is in contrast to what you typically see with survey flights. Not that survey flights are not good. You need survey flights for a variety of applications, but those are typically maybe 100 meters or maybe tens of meters up in the air. And we're talking about things that are very close to get very close views of things. And I won't go into too much detail here, but essentially, as I said, we've been working on this for a couple of years now. And so we've got multiple generations of the flight stack that we've developed for these purposes. And the platform that we used for the contest and that we're using today is a DJI platform. It was an M100, as you're aware. The same flight stack and the same software could work on an M600 as well. It contains a typical sort of camera. It could use any of the Zen-use cameras. And in addition, we use the guidance system, if you're familiar with that, which is a series of stereo cameras that you can also install. It has stereo cameras on the edges, but also a ultrasonic sensor in the middle. And you can place those in various positions around the drone and use them for stereo vision. In addition, which is also very important, there's a companion computer. In the case of the contest, we used the Manifold, which is also from DJI. It's basically an NVIDIA K1 based processor with lots of GPU power, which you might imagine is necessary for doing some of the computer vision things that we were doing. And in some cases, you'll see some of the videos where we actually had installed a cellular broadband modem as well, so we could transmit real-time imagery back to a remote operator. So the flight stack itself, as I've mentioned a few times, it relies very much on the DJI SDKs. It uses the mobile SDK, it uses the onboard SDK, and also uses the guidance SDK, which really hasn't been talked about today, but there's an SDK for the guidance system as well, which we used. We were big fans of open source software, so we use Ubuntu, OpenCV, ROS as well. So we use a variety of open source software packages to put this flight stack together. And in addition, since we're able to get really close to things, we're actually able to collect some high resolution imagery. And so we've got some technology and stuff as well for presenting this imagery in conjunction with maps, whether it be stills or videos, and you'll see some of that as well. So basically, when we talk about the key drone technology that we developed as part of this contest and in conjunction with what we're doing, you've got the sense and avoid, of course. You've got asset detection, which is represented in terms of being able to detect targets and so forth, and be able to track the targets and do flight control with respect to the positions of the targets and so forth. We have low altitude terrain following. As you saw, the drone was flying relatively low to the ground in order to see the survivor tags. So terrain following actually, as most of you are probably aware, is actually a pretty difficult problem with drones because height using the barometer is not a very accurate thing. GPS tends to be inaccurate sometimes. So we actually use computer vision to do our terrain following and stuff as well. We have the ability to plan autonomous missions. In the case of the contest, there was actually a search path through the search area that was generated. So the drone was actually trying to follow a search path, and then as it encountered obstacles, it would deviate from the search path in order to try to do sense and avoid on the obstacles, but then try to return to the search path and continue on the search path. As I also mentioned, there's real-time command and control. So potentially you're transmitting back real-time imagery to some operator portal, and potentially you can even give commands remotely to actually control the drone's position and so forth in relation to targets that might be tracking and things like that. There was dynamic launching and landing off moving platform. And of course, as I mentioned, we can also visualize things in conjunction with maps and all this imagery that we're collecting. As we move down the road and do some more development, we'll probably start looking at different types of analytics for various specific vertical marketplaces. But right now, we've mostly been about the flight stack and the collection of the imagery itself. And so what I'm going to show you now is a video which shows in a little more technical detail about some of the things that you've seen. So for instance, the tracking. This was a very, very early version of the tracking software that we developed. In fact, you might notice this actually isn't even a DJI drone. This was before the M100 was actually available. And so what you're going to see here is the ability for the drone to take off upon a command from a remote operator. The console on the right-hand side there is the actual remote operator's browser-based console. the operator will be able to give commands as to which of these targets the drone should be tracking, and then give additional commands to have the drone move closer or farther away from that target. So this is kind of a demonstration or example of what you might call semi-autonomous flight. So the drone itself is actually flying autonomously. It's tracking the target. All this is running on the vehicle itself. But then the operator is actually able to adjust to give it high-level commands like move closer, move to this target, and things like that. Which is what you're really going to need to have a truly remote pilot, controlling a drone. So he's not actually flying it, he's actually giving it commands. As you can see, the image is the target itself is being highlighted. The drone is going to try to keep it a certain aspect ratio that's been commanded by the remote pilot to maintain. You can see that the drone itself has maintained that aspect ratio with the target, so even though the target's moving, the drone will maintain that aspect ratio with the target. So you can imagine you might want to do something like this if you were inspecting a remote asset somewhere, have some sort of pattern potentially, or maybe there's some aspect of the asset itself that the drone can pick up using computer vision. Here's the same sort of thing using the M100, which when it became available about 18 months ago, we started porting all of our stuff to the M100. This is our lab up in San Rafael. Okay, so for sense and avoid, what you're going to see here is this 4-panel. We've got our motion planning there on the right-hand side, so that this kind of shows in a little more detail what the motion planning is doing. On the left-hand side, you've got your optical detection, so you can see there's some point clouds there that's being generated by the stereo cameras. Those point clouds are then being mapped through this 3-dimensional occupancy grid, and then the motion planning is then using the occupancy grid to plan paths around obstacles and so forth. We support autonomous missions with this flight stack. So in this case, there's a levee. And this is also an example of a remote pilot who's actually sitting back in our hangar looking through this portal here on the right-hand side. And this is an example of real-time imagery being transmitted back using a cellular modem to this drone, which is flying autonomously along the levee, collecting imagery of the levee. All right, here's some visualizations. So we can collect the data, whether it be videos or stills. And in the case of videos, we can obviously geocode and geotag the videos, so we know precisely where that video was captured. So here's a case where levee, so the operator might want to be able to scroll back and forth through the video quickly on the map and see where it was taken. Here's the kind of very close range oblique imagery you can take when we fly very close to things. So this is the case. This is an example of a vineyard. We're able to fly very close to vines and get these close-up images and then geocode them and tag them. So you can find out, almost like a street view sort of view, we call it ground view perhaps. And then of course we have the ability to do terrain following and row following. This is an example of our advanced terrain following where we're actually able to, this is all totally autonomous, we're able to not only fly a certain height above the ground, but also be able to pick up the rows using computer vision and then maintain the drone in between the rows. I believe these rows are maybe 3 feet wide, they may be 4 feet wide. But as you can see, it maintains a pretty steady flight. It stays between the rows and it's able to capture a variety of imagery and video and so forth. So just to give you a sense of how this might be applied in one of the areas that we're currently looking at, we actually work with UC Davis right now. They're one of the most renowned enology departments in the world. They're developing a variety of sensors for vineyards and so forth and looking at ways to try to get those sensors as close as possible to the vines. So we're working with those guys. We also have a couple of vineyards that we fly with. There's Clos de la Tech down in Santa Cruz that we fly with and do a lot of experiments down there and so forth. But again, in this case, we're trying to get as close as possible to the vines to get very oblique imagery and so forth. And of course, the benefits of doing this, in terms of inspection, right now they send workers out into the field pretty much every week, every 2 weeks to do a variety of types of inspections. And they typically don't walk the entire fields. They typically do these random samples. So this is a case where we have the potential of having a drone potentially go down the rows, collect all the detailed imagery, potentially then do some analytics on that to look for fungus or irrigation leaks or whatever that might be, but also give the ability to actually go out there and look, do a ground view type of thing where they can actually click on images and see the images close up if that's what they want to do. So there's a whole variety of different types of applications that you can do this if you can fly fairly close in an autonomous fashion. I mean, in fact, our vision is that at some point, probably some number of years from now, when the FAA starts allowing more autonomous types flights, that there will be drones hangared in a variety of locations, maybe on vineyards, maybe on top of people's houses, maybe in every substation, that remote pilots will be able to then launch and run very specific missions, be able to fly close to things and so forth, maybe do some high-level survey flights if necessary. But our vision is that's the way that these things will be operated in the future. And so we're working very diligently to try to develop some technologies that will support those sort of use cases. We know that a lot of those things aren't quite there today yet, and we know that the FAA requires remote pilots to be at the site in terms of visual line of sight and so forth. But that's going to change over time. And in order for it to change, you need to be able to support things like semi-autonomous flight and things like that, and then be able to prove that these things are safe. So in closing, I will show you a quick video of one of the vineyards that we fly. This happens to be the steepest vineyard in California. It's a 45-degree slope. This is the one at Clos de la Tech down in Santa Cruz. These rows, I believe, are 3 feet, very narrow rows. And the drone picks up these rows and then tracks them, maintains a fixed height above the ground, and is able to pick up some pretty interesting imagery. Again, this particular application is row following. And of course, every domain, depending upon what sort of asset you might want to be tracking or get close to, may have different requirements, and you may require different sort of training on the computer vision to be able to pick that asset up and fly close to it and so forth. But we think this has a lot of great potential in terms of those sorts of applications.